Hello and welcome to Topic 6, Series Expansions of Complex Functions. Now you'll remember from our discussion at the end of Topic 3 that locally convergent power series define complex analytic functions. And you'll also remember back in Topic 2, we saw how to Taylor expand real functions. This gives a power series where the coefficients are given by different order derivatives evaluated at the expansion point. In this topic, we're going to see how complex functions can be Taylor expanded in a similar way to real functions in regions of analyticity in the complex plane. We're then going to extend this discussion of series expansions to functions in regions of non-analyticity. And this will give us something called Laurent series. These contain positive and also negative powers of the complex variable z. In this first video, we're going to use Cauchy's integral formula to derive Taylor series of a complex analytic function. From the previous topic, you'll recall that this Cauchy integral formula relates the value of a complex function, a complex analytic function, at some point to its value along a closed contour enclosing that point. We're going to generalize this to show that actually the values of all of the function derivatives are also specified in this way. This will allow us to define Taylor series for a complex analytic function. These are the intended learning outcomes for this video. So after watching this video, you should be able to use the generalized Cauchy integral formula to compute contour integrals. And you should also be able to find the Taylor expansion of a complex analytic function. And with that, let's begin.
In this video, we're going to look at the Taylor series of complex functions. Now, in the previous topic, in topic 5, we derived Cauchy's integral formula. I'm going to abbreviate this to the CIF, and I'll write it down here. We have that the integral along a closed contour C of f of z divided by z minus z0, where z0 lies within the contour C, that was given by 2 pi I times the function value at z0. For what follows, it's going to be useful to re-express this by changing the variable labels, and that will become clear in a moment. I'm going to say, now let us rename variables and write this as, so the relabeling I'm going to do is I'm going to relabel z0 as z, and I'm going to relabel z in our original expression above as w. Performing this relabeling, we obtain that the function value at an arbitrary point z within the contour C is given by 1 over 2 pi I, and then we have the integral over our closed contour C of the function evaluated at w over w minus z dw. I'll draw a picture to show what this means. We have our complex plane, real and imaginary axes. We now have a point labelled z, and our contour C, which might look something like this, oriented in the anti-clockwise sense, A point on this contour is labelled by W. So W is constrained to lie on the contour, which I'll label C, and Z is a point inside. I'll write that down. That the new form that we've written Cauchy's integral formula in, this is valid for all Z within the region over which F is analytic. And in this case, Z lies within our chosen contour C. When written in this way, the non-local character of analytic functions is clear. If we look at the right-hand side of the rejigged Cauchy integral formula, we have a contour integral along C of f over w minus z, where the integration variable w is constrained to lie on the contour C. So the right-hand side tells you about behaviour on the contour. I'll write that here. Right-hand side is behaviour on C. On the left-hand side, we have the function value at some point z, which we've labelled in this diagram. That means the left-hand side tells you about the value within the contour. I'll write this down in words as well. The value of our complex function f at a point z can be computed by considering the value of f on an arbitrary closed contour enclosing z. The reason I've done this relabeling is because we're used to thinking of z as the label for the point that we're moving around in the complex plane and investigating the function behaviour at. Okay, so we've re-expressed Cauchy's integral formula in a slightly different way. For the rest of the video, I'm going to use this to demonstrate the analyticity of our complex function f directly. I'll write the Cauchy integral formula can be used to demonstrate the analyticity of f directly. You'll remember our discussions of the analyticity of f in our derivation of Cauchy's integral formula in the previous topic. Okay, how do we proceed? Well, let's suppose that our complex function f is analytic on and within a circle. It's important that it's a circle. We'll see why later. Centered at some fixed point z0. I'll draw a picture and dispense with the axes to make it a bit clearer. We give ourselves a circle, make it quite big. This circle we're going to label as a contour C, and it's oriented as usual in the anti-clockwise sense. This circle is centered at the point in the complex plane z0, we're going to label points around the contour C using the letter W, as we did in the picture above. And we're now going to be looking at the behavior of the function at some point z that we are free to move around within this circular contour. So I'll label z over here. I'm also going to label the distances between various points. Here we have this as the distance given by the absolute value of z minus z0. Similarly, this distance between z0 and w is given by the absolute value, or the modulus of the complex number w minus z0. The last thing I'm going to label on this diagram is the nearest point at which our function fails to be analytic. I'm going to put it out here for now, and we'll come back to that later. I'll label it z1, and this is the nearest point where our function f is not analytic. As a little note to the various meanings of the points I've labelled, I'm going to say that z0 is fixed, w lies on the circular contour C, and z is a point we can move around within the circular contour. Immediately, you'll notice that as a result, the distance given by the absolute value of z minus z0, as labelled in this picture, is always going to be less than the distance w minus z0. And that's because z always lies within the circle, and so the distance between it and z0 is always going to be less than the radius of the circle. You'll also note that where I've drawn z1 outside the circle means that this also holds. This is less than the distance between z1 and the centre of the circle. We'll come back to the relevance of these distances later. Okay, with this picture in mind, let's apply Cauchy's integral formula as we re-expressed it a little bit earlier. Applying Cauchy's integral formula, that states that the function value at the point z is given by 1 over 2 pi I, the integral along our circular contour C in purple of f of w, where w lies on the contour, divided by w minus z. This is now an integration with respect to the variable w. We can rewrite this, keeping the 2 pi I out the front and the integration contour the same. I'm now going to add and subtract z0 inside the denominator, and the reason for doing so will become clear in a moment. The numerator is going to stay the same, f of w. On the denominator, I'm going to take w minus z0, and I'm going to subtract z minus z0. And you notice that taking into account minus signs, the z0s cancel. So we haven't actually changed anything in going from this first line to the second line. Continuing on, we have 1 over 2 pi I, the integral along C, we have f of w, and I'm now going to take out a factor of w minus z0 out the front in the denominator, and that's going to leave us with 1 over The first term in the denominator is w minus z naught, so we have 1. And then we have minus z minus z naught divided by the term that we've taken out of the front, w minus z naught. Why have we done this? Well, from our picture, above, recall that we had the distance between z and z naught was always less than the distance between w and z naught. And that held for all z and w that we specified. That's because z is within the circle C. Looking at the last term in the integral, you'll spot that this looks very much like the limit of a convergent geometric series. And that's because the absolute value of z minus z naught divided by w minus z naught is less than 1. I'll write that here, i.e. z minus z naught over w minus z naught, absolute value is less than 1. Therefore, we have a convergent geometric series. You remember we looked at this in topic 3 when we looked at the convergence of complex power series in the last video. What does this mean? This means we can write the term in the integral given by 1 over 1 minus z minus z naught over w minus z naught. We can write this as a convergent infinite geometric series where the terms are z minus z naught over w minus z naught raised to the power n. And we note again, this geometric series converges when the absolute value of z minus z naught over w minus z naught is less than 1. And that comes from applying the ratio test. Okay, substituting that into the expression above, continuing on, we now have that the function value at a point z is given by 1 over 2 pi I, the integral along our circular contour C of f of w over the w minus z naught that we took out the front, and then we can insert our geometric series. This integral is with respect to the variable w. If you look at this expression, we have the integral of a sum of terms. And it turns out for this expression, we can interchange the order of summation and integration. Here, the integral of sums is the same as the sum of the integrals. I'll write that down. We may interchange the order of summation and integration. And that's because here the integral of the sum is the same as the sum of the integrals. We also say this is a uniformly convergent sum. That's the reason we're allowed to do this. Doing that means that we have f of z is now given by a sum from n equals 0 to infinity of z minus z0 terms that we take out the front times 1 over 2 pi I the integral of f of w over w minus z0, where the power is now n plus 1. And you'll see that from the line above. We had f of w divided by w minus z0, and then within the sum we've got w minus z0 to the power of minus n. We've taken the z minus z0 to the n outside the integration, because the integration is with respect to w, and we've attained the line below. You'll spot that this is a power series in the variable z minus z0. This will become even clearer if we write it out like this. This is the sum from n equals 0 to infinity of z minus z0 to the n times some coefficients we index with n. This is precisely a geometric power series that we saw at the end of topic 3. And here, the coefficients Pn 1 over 2 pi I, the integral along our circular contour C of f of w over w minus z0 to the n plus 1 dw. I'm going to put a blue box around this because we'll return to it later. The last point to make here is that these coefficients must be such that the power series converges, because we know that the function f is analytic by hypothesis. I'll write that down. These Pn must be such that this power series converges. That's because f is analytic by hypothesis. So the ratio test should tell us that this complex power series converges, and it must converge to a well-defined value because f is analytic. And you remember that we specified analyticity means differentiable and single-valued. What does this mean? Well, this means that we have shown explicitly that the sequence of integrals in the blue box, Pn, those are well defined. We're going to make an interesting connection to these integrals Pn. Let's take another look at Cauchy's integral formula. You remember f of z is given by 1 over 2 pi I. The integral around our contour C of f of w over w minus z dw. You'll notice that the only z dependence on the right-hand side of this expression is in the denominator of the integrand, and that means that we can do something called differentiate under the integral sign. I'll write that out and then show you what it means. Note that the only z dependence on the right-hand side of Cauchy's integral formula, as written, it only occurs in the denominator of the integrand. This means that we can do something called differentiate under the integral sign. What does this look like? Well, if we differentiate the expression towards the top of the page, we get that the derivative of f of z is given by the derivative with respect to z of whatever's on the right hand side. So 1 over 2 pi I, the integral around contour C of f of w over w minus z dw. We can move that derivative inside the integral until it hits the only z dependence there. We have 1 over 2 pi I, the integral along C, f of w is unaffected, and then we have d by dz of 1 over w minus z. And this is still an integral with respect to w. We note that we can write this as d by dz of w minus z to the minus 1. We know that we bring the minus 1 out the front, and this gives us minus 1, and then times the derivative of what's inside the brackets, which is also minus 1, and then w minus z now to the minus 2, so that the minus signs cancel. We're therefore left with 1 over 2 pi I, the integral along C, f of w over w minus z squared dw. And this is our derivative f primed of z. You can also show this statement holds directly by using the definition of a derivative as a limit, and the associated problem sheet asks you to do that as one of the exercises. Okay, so we've expressed the derivative of our function at a particular point z in terms of the function value at a point w lying on the integration contour C. Again, the non-local property of an analytic complex function is obvious. We can get even more out of this result. We can carry on differentiating with respect to z in order to get the nth derivative of our complex analytic function. And the following can be proved by induction, but I'm just going to write it down. You can show that the nth derivative of our function at some point z is given by n factorial over 2 pi I, the integral along some closed contour C, f of w divided by w minus z to the n plus 1. You can verify that's true for n equals 0 and n equals 1 above. This is a very important result called the generalized Cauchy integral formula. And I'll repeat that this again reflects the non-local character of complex analytic functions. Knowing the value at the points w on the contour C lets you calculate all derivatives of the function at some point z lying within the contour C. I'll write this down. Hence the assumption of analyticity of f on and within C is sufficient to guarantee the existence of all derivatives of f. So of derivatives of f to all orders. This is a really remarkable result, but we're not done. There's another remarkable point to make. I'm going to write down the integrals Pn that we had earlier in the blue box. So recall from earlier, we had that Pn are given by 1 over 2 pi I, the integral along our circular contour of f of w over w minus z naught to the n plus 1 dw. And that was of interest because we had f of z expressed as a power series with these coefficients and in terms of z minus z naught. Now, looking at what's in the red box and the integrals Pn I've just written down, you'll see that these are exactly the same integrals. The only difference is the factor of n factorial. I'll write this down, this is very important. Notice that apart from a factor of n factorial, these nth derivatives are exactly the same integrals defining the Pn coefficients in our complex power series earlier. Given the power series expansion of our function that I've underlined in blue, we can now substitute in for the coefficients Pn in terms of the nth derivatives in the red box. Finally, this allows us to obtain the Taylor series for a complex analytic function. Therefore, arrived at the Taylor series for a complex analytic function. From our power series underlined in blue, on the left hand side we have our function, and on the right hand side we have the sum from n equals 0 to infinity, and we now substitute in for Pn in terms of the nth derivatives at the top of the page and account for the factor of n factorial. We obtain the nth derivative evaluated at the point z0. You'll notice this by looking at the denominators of the expression in the box at the top and the denominator of the integrand for the coefficients Pn. So we have the nth order derivative evaluated at z0 divided by n factorial, and then multiplying, looking back at the power series, z minus z0 to the n. This is another incredibly important and remarkable result that I'll put a red box around. This is the Taylor series for complex analytic f of z. So this means that just like for real functions of a real variable, to find the Taylor series we repeatedly differentiate the function and plug it into this expression in the red box. I'm going to make a short point about convergence of this power series representation. Note that it was critical that the analytic region we defined earlier, and I emphasised this at the time, was a circle. This is because otherwise the geometric series that we found used might not converge. That was our discussion of the distances z minus z0 and w minus z0. Now this circle we defined earlier, this is the circle of convergence. For the complex Taylor series. And its radius is the radius of convergence. And from our picture earlier, where we had the point z1 lying outside the circle as indicating the first point where the function is not analytic, we know that the radius of convergence is equal to the distance from the expansion point we can read that off from the expression in the red box. The expansion point is z0. That's also clear from how we wrote down the complex power series. So the radius of convergence is equal to the distance from the expansion point, z0, to the nearest singularity. So in the picture earlier, we could have taken the circle to have a radius, so it was just not overlapping with that point, Z1. In general, the Taylor series will diverge otherwise. So it will diverge outside this circle. And for points on the circle, you have to check. It may or may not converge. And this will remind you of our discussion of the ratio test, where if the test is ambiguous, you have to check explicitly for convergence. I'm next going to remind us what we meant by an analytic real function earlier in topic 2. Earlier we said that a real function of a real variable f of x is real analytic if all its derivatives exist and it has a real Taylor expansion with non-zero interval of convergence. And back then we defined such intervals on the real number line. So that was our definition of what it means for a real function to be analytic. We can analogously define analyticity of a complex function in terms of its complex Taylor series. So here, a complex function of a complex variable f of z is analytic if it is infinitely differentiable We saw that in our power series expansion of the complex function, the sum runs from n equals 0 to infinity, and we need the nth derivative. So therefore, a complex function of a complex variable is analytic if it is infinitely differentiable, and it therefore has a complex Taylor expansion with a non-zero radius of convergence. And given it's a complex function, we talk about convergence in the complex plane. That's a lot of text, and I would encourage you to read through that in your own time, again, to make sure it makes sense. Right, to end this video, we'll go through a quick example of finding the Taylor series of a function about a point. Let's consider expanding f of z is 1 over z in a Taylor series about the point z0 equals 1. As always, I'll draw a quick picture. We have the real and imaginary. Our expansion point, z0, lies here. And we notice that the closest singularity is at z equals 0 here. This is our first point of non-analyticity at z equals 0. That means that we can immediately draw our circle of convergence as a circle with radius 1 centered on z0 equals 1. Something like this. So this is our circle of convergence that we expect. And we can also label the radius of convergence of convergence. Okay, let's proceed. From above, we have that the complex Taylor series is given by f of z is the sum from n equals 0 to infinity of the nth derivative evaluated at z0 divided by n factorial, and then this is an expansion around the point z0, so we have z minus z0 to the power of n. Well, we need some derivatives. We can have n and the nth derivative of our function, 0, 1, 2, up to n. Our function is z to the minus 1. Differentiating that once, we get minus z to the minus 2. Differentiating again, we get 2z to the minus 3. And continuing on, you can convince yourselves that the nth derivative of our function is given by minus 1 to the n times n factorial. You'll see that we keep bringing down n factors of n, and then times z to the minus n plus 1. Putting this into our expression for the Taylor series at the top, we therefore have that 1 over z is given by the sum from n equals 0 to infinity of the nth derivative evaluated at z0, which is our point 1, divided by n factorial, lots of z minus z0 to the n. Putting in the line above, we have minus 1 to the n times n factorial times, and then z0, and then we substitute in z0 as 1 to the minus n plus 1, divided by n factorial times z minus 1 to the n. And tidying this up, so cancelling factors of n factorial and sorting out minus signs, we're left with the sum from n equals 0 to infinity of 1 minus z to the n. In other words, 1 plus 1 minus z plus 1 minus z squared, and so on. This is our Taylor series expansion of the function 1 over z about the point z0 equals 1. And earlier we drew our circle of convergence, and this can also be tested with the ratio test. We note that as long as the absolute value of 1 minus z is less than 1, we know this geometric series converges. And that's tested using the ratio test, but it's also in agreement with our circle of convergence that we obtained by looking at the nearest singularity at z equals 0. Looking at our representation as an infinite sum in that last line, we also know this sum can be performed explicitly. We can look at what value that sum approaches in the limit. The reason we can do that is that power series, the sum from n equals 0 to infinity of 1 minus z to the n, well, that's analogous to the complex power series that we saw at the end of topic 3. Since we know where this power series converges, we can consider the limit of the partial sums in the same way as in the second video of topic 2, and that would allow us to establish the value to which it converges. I'll write down what I mean and also relate the connection to our discussion in topic 3. So we can perform this sum. The sum from n equals 0 to infinity of 1 minus z to the n is given by 1 over 1 minus the variable in this power series, which is 1 minus z. This simply yields 1 over z, which is exactly as expected. That's the function we wanted to take the Taylor expansion of. I'll note in the margin, recall from topic 2 that the sum from n equals 0 to infinity of t to the n was 1 over 1 minus t. This is analogous to that, but we're now extending to complex variables. Now, this is one way of finding the Taylor expansion of a complex function by finding the derivatives. There's another way which is also useful. Another way to approach expansions about z0 that is useful. Effectively, we're going to do that last step of identifying a geometric series in reverse. It's going to be helpful to define epsilon as the complex number z minus z0. And in this way, epsilon is small. That means that the point z, given by z0 plus epsilon, is within the circle of convergence for whatever function we're trying to Taylor expand. With this definition of epsilon, the task now is to look for a geometric series in powers of epsilon. So now, look for a geometric series that you can expand in powers of epsilon. You had a bit of practice at spotting these in the problem sheet for topic 2. Okay, so for our above example, z0 equals 1, and we're interested in expanding f of z equals 1 over z. We can coax this into looking like a geometric series as above by taking 1 plus z minus 1. Z minus 1 is the definition of our variable epsilon. This is the limit of a complex geometric series. We know that this is the sum from n equals 0 to infinity of minus epsilon to the n, and that converges when the absolute value of epsilon is less than 1. Substituting back in epsilon in terms of z, we can write this as the sum from n equals 0 to infinity of 1 minus z to the n. And if we were to write that out, we would get 1 plus 1 minus z plus 1 minus z squared, and so on. We finally note that this agrees with our Taylor series. So either you can perform a Taylor series explicitly by differentiating repeatedly, or you can try coaxing a geometric series you know how to evaluate to be an expansion about the point you need. That's the end of this first video of topic 6. As a quick recap, we've seen how Cauchy's integral formula can be used to derive Taylor series expansions for complex analytic functions. Along the way, we also derived the generalized Cauchy integral formula, and as well as noting the similarity between analytic real and complex functions, we were also interested in the radius of convergence for such an expansion. Thanks for listening, and up next is the second video of topic 6.